Good morning. Good morning, good afternoon, good evening. It's another Wednesday. It's another episode of the Wednesday or Weekly Tech Forum, sponsored by Love My Tool. But today we are at the beginning of a new era. We're actually trying something a little bit different. We call it the Sharkfest.tv. You can actually visit us uh, by typing the URL sharkfest.tv. The idea is that Tim and I have been using this Google Hangout and doing the video for a variety of purposes. We did interviews, we do technical presentations, we even did live demos. And along the way, we thought about Sharkfest. Tim has been involved with Sharkfest from the beginning. I've been a participant of Sharkfest as a vendor back in the days. And one of the things that we walk away from Sharkfest is that it's a very unique forum. It just somehow turned into a place where people meet friends, both new and old, and people learn things, both new and old. And there's a part of it that I think is very valuable, which is that it's a vendor neutral forum. People were there to sell the product, but not in your face. They really are there to build value. So Tim and I thought about this and said, well, how about we just do something like that? We invite some of our sponsors and maybe even our writers, and just for once do something that is just for education. And so we thought about DC, and we invited him to kick off this series for us. And in fact, we liked Sharkfest, and we admired the people behind Sharkfest so much that we came up with a tagline, which is that if it's not good enough for Sharkfest, it's not good enough for Sharkfest TV. So with that, I set a very high bar for DC. Good morning, DC.
Good morning, Denny. How are you?
Good. And good morning, Tim. Good afternoon, Tim. So DC, I am very grateful that you accepted our challenge, and I know you set a high standard for yourself as well. But talk to us about what you have in mind, and I know you planned a series of these lectures. And tell us why you think these basic knowledge is important for the industry.
All right. Well, thanks, Denny. I'm honored to have been invited to give these presentations. As you and I and Tim have been talking over the past few weeks, there's a lot of people at Sharkfest and in the Wireshark community, as well as the broader networking community, that are experts at the operations of networks, that know how to set up routers and switches, set up endpoints, have Cisco certifications, and really know everything about how to actually operate the day-to-day things that need to get done on a network. But for one reason or another, possibly because they don't come from a computer science background, or even if they do, had a class in networking 10, 20 years ago and haven't opened their basics of TCP/IP books since then, may not have a good foundation in the basics, or need a review of those basics. So what I'm trying to focus on in this series is what is going on inside your network. How are these devices communicating with each other? What are those packets that are going over the network? And how does the applications and the networks work together to cause performance issues, and how can those performance issues be resolved? So that's kind of the flow of what we're looking at. What I'm going to start off today with is the very basics of the overview of networking itself and the OSI stack and the things that are related to that. So unless you have particular things you want me to comment on, I thought I'd just go ahead and get started.
Yeah, go ahead and get started. I'm anxious, personally, I'm anxious to learn something today. Thank you.
Get the sharing working properly. Are you able to see my screen share?
Oh, this is perfect. You got it right.
Okay.
Yes.
So my name is DC Palter. I'm with Apposite Technologies. We make network simulators, but I'm not going to talk at all about our products here today. I'm going to be focusing on teaching the fundamentals of TCP/IP networking. Most of this is based out of classes that I've given at UCLA and the Pentagon, and actually wrote a little textbook on these topics. So I had a lot of this information available, made it easy to put this together. So the overview of the series, which is going to run for a few weeks, I think the plan is to do it once a month if we can, is start off talking about networking layers, the very fundamentals of networking, then focus in on TCP/IP in general, and then look at the specifics of IP, both IPv4 and IPv6, then the transport layer protocols, UDP and TCP, and then move up to the upper layer protocols of the different application protocols, and then look at how that affects application performance and what can be done to improve that performance. So today we'll start off with the OSI 7-layer model, just because every discussion of networking has to start with the OSI 7-layer model. I don't think that's a very good model for today's network, so we'll transition then to the Internet 4-layer model, which people don't talk about nearly as much. And we'll talk about what these layers are, and then networking protocols in general, and then look at what I think is the most beautiful thing in networking, the IP hourglass. So there are, in the OSI model, which was developed right about the time that TCP/IP was being developed, actually by mostly a different group of people, they came up with the 7-layer model. And there are, as you can imagine, 7 different layers, starting with the physical layer, or the PHY. The physical layer are the actual wires that are transporting electrical signals or optical signals between 2 devices. So these are your wires. But it is a bit of a misnomer because it's not necessarily physical. It may be a wireless network, but it is the actual movement of bits. The next layer is called the link layer, and this is the interface between the devices and the physical layer. So this is the part that will take the data and frame it in order to send it over the physical layer. The data link layer operates as a single hop between 2 devices. This might be a point-to-point connection between 2 T1 modems, or it might be a shared system like Ethernet, but it is between a PC and a router, or between a switch and a router, or a switch and a switch. It is always between 2 physical devices that are connected by the physical layer. Next, we move up to the network layer, which in a modern network is IP, but it wasn't always IP. The purpose of the network layer is to direct packets through this network that we've created of physical devices. So a real network may have a couple of end nodes, but in the middle there's lots of switches and routers and maybe firewalls and everything else as the packet goes hop to hop. And we need to move the packets between one side to the other side. And the network layer is responsible for moving packets of data from a source device to a destination device across a network of systems in the middle. So in other words, this is the layer that's responsible for routing or switching, is another way to think of it. Next, we move up to the transport layer. The transport layer controls the end-to-end transmission of data across the network. So the network layer is just moving a packet from one hop to another hop and directing it to get to the next hop. The transport layer is where we have communications between the 2 end nodes. So if you think about things like reliability, about the packets getting out of order, about packets getting lost, about things getting corrupted, about controlling how much data will be sent at any time so you don't overrun the network in the middle, that is all handled by the transport layer, or can be handled by the transport layer. And these are the things the transport layer needs to do, is the communications between the source and destination devices. On a TCP/IP network, that is almost always TCP for what's called reliable transmission. We'll talk about what that means later, or UDP for unreliable transmission. That doesn't mean that it's bad, just it's not designed to have acknowledgments, and it's okay if you lose things. So it's called an unreliable network. We'll talk about that when we focus in on the transport layer. Next, we have something called the session layer. The session layer, at least in theory, is responsible for establishing and terminating connections between the end nodes. This was envisioned as a separate layer, but really it's part of the TCP/IP protocol and is handled at the transport layer within TCP/IP. There are other protocols that handle things differently, but within TCP/IP, the session controls are handled within the transport layer. Similarly, the presentation layer, in theory, is responsible for translating the data format used by the sender into the format used by the receiver. And that can mean things like compression or encryption, which were supposed to happen at this layer, but in reality, in modern networks and TCP/IP networks, happens either at any of the lower layers, and this translation layer there's nothing that really fits in there. And then lastly, we have what's called the application layer. Most people confuse that and think of that as the application, but it's really not the case. It's the application layer protocol. And a good example, or good examples of this, would be FTP, HTTP, or SMTP for email. These are the protocols used between a client and server so that they can communicate with each other. It's not the actual application data itself. It's a protocol designed so that you can have interoperable applications, so that one web server can communicate with a web client. They don't need to come from the same manufacturer. We have protocols for these things. So that is the 7-layer OSI model. There was a set of protocols called the OSI, or gossip protocols, that were designed around this way of thinking. They were supposed to take over the world, and nowadays most people have never heard of them because they turned out to be rather clunky and expensive. And so what we ended up with was TCP/IP, which was free and interoperable, and everybody had it. And it works. The basic concept's the same, so we still use this OSI model. That's what they usually teach in computer science. But in reality, what we have is, from the TCP/IP way of thinking, is a 4-layer model. We have the internet or IP layer. We have the transport layer, which is the TCP or UDP protocols. Below that, we have the network interface, and that can be Ethernet, that can be your cell phone wireless 3G, 4G network, that can be your DSL modem, it can be a satellite network, it can be anything, as long as the two sides can communicate with each other. And above that, we have the application layer protocol. So still a lot of times manufacturers talk about optimization, being a layer 3 device, or layer 4 device, or layer 5 to 7 device. So we still use this OSI model, but in reality, it's probably better to think of it as we have an internet layer, we have a transport layer, we have an application layer, and then we have the physical network below that. So how do these layers get used in practice? When we look at real packet traces, we see exactly this, that we have layers of information within information. And this is the way a modern network works. If we look at an Ethernet packet, inside that Ethernet packet has an Ethernet header and an Ethernet payload. The Ethernet header has the source and the destination MAC addresses, which are the two physical devices which are communicating in that one hop. Inside that, we have a payload, and that payload includes the IP packet. The IP packet has the IP header and then the IP payload. Within the IP payload is the TCP header, and then the application data, which may include the application protocol. So when we look at this within Wireshark, Wireshark is very, very handy for being able to deconstruct this into the different layers so you can see what's going on at each of these different layers that you may care about. To complicate things, one packet, one TCP datagram does not have to fit within one IP packet. So things can end up getting split up. So it's not always as clean as this, but this is the basic idea that within a link layer packet or datagram, as it would be technically called, we have an IP packet, and within that we have a TCP or UDP packet. Within that we have the application protocol, and within that we have the application data. And we can break those things down and see the individual layers depending on what we want to look at. For the rest of this series, we'll be talking about TCP/IP because that's the only thing anybody cares about anymore. But from a historical perspective, TCP/IP wasn't the first protocol, and it wasn't the only protocol, and for a while it wasn't even the most important protocol. There have been a lot of other protocols over the years, and for a while, pretty much any manufacturer of a network of computers and possibly printers and file servers had their own protocol. So Apple, for a while, you would connect an Apple Macintosh to an Apple printer, possibly to other Apple Macintoshes, and it all ran over AppleTalk, and it could talk to other Apple-specific devices, couldn't talk to anything else. Same thing if you had VAXs, they talked DECnet. The original file and print share for enterprises was NetWare, and it ran a protocol called IPX-SPX, which was a variation on XNS, which Xerox invented, and was used for Xerox. The original PCs were really mini computers talking to Xerox printers. So there are a bunch of protocols that were out there. Some of these were standardized so that anybody could use them. Some of these were proprietary for particular manufacturers' devices. Some of them were routable, meaning you could have networks that could be complex networks that may go over physical geographies, or they were really designed for one small grouping, like SNA, of a group of terminals talking to a mainframe, which might be in a different physical location, but it was always one set of devices, one network talking to one mainframe. I mention this just because a lot of the thinking of networks came out of these earlier protocols. When TCP/IP was developed, it was just one of these protocols. It was the one that was built into Unix. It was available for free. Most of the academics had it. It was good for research. It was good for researchers to communicate with each other, and it was free and it was available to everyone. And that became kind of the key to why it took over the world. Just because it was available, we ended up with this network of all these universities that were communicating with each other, and people wanted to tie into that, so they used TCP/IP, and we ended up with this ubiquitous network of IP nodes that would communicate with TCP/IP that built on top of that file sharing, printing, and email, and suddenly we had the internet, and that took over the world. So we have something that I call the IP hourglass. And this is really why, at least in my opinion, the internet has been so successful. We now think of it as being obvious that this is the way things should work, but it wasn't the way things originally worked. That we have this one layer, that's IP, that every device has, and everyone can communicate with every other device in the world because it is all going over this IP network that can get one packet from one place to another place. On top of this, and those devices in the middle don't know anything except the IP protocol, which is pretty simple, that says a packet comes in one port. I've got a table that tells me which interface to send the packet out, so I can get to the end node. So we just end up with these packets going hop by hop from router to router till they finally reach the end nodes. The end nodes don't know anything about what's going on in the middle, but they have a choice of TCP For applications that require reliability, every packet has to be delivered before we can use it. For UDP, which is for real-time applications that we care more about just dealing with stuff as it arrives. We don't worry about things if they arrive out of order. But every end node has it so that every device can communicate with each other using TCP or UDP. And that gave application developers running, didn't matter whether they were on a Unix machine or a Linux machine or a VAX or a PC or a cell phone, they all had TCP IP, they all had TCP and UDP, and so we could write applications on top of that that could do anything. So application developers don't really need to know anything about networking other than how to hand the data off to the network layer, and it takes care of everything below that. So people can focus on developing voice applications or email or file transfer or pretty much anything that in our modern internet we have running. The application developers can focus on their specialty, and below that they just have a service that takes the traffic and takes the data and delivers it to the other side. Underneath IP, as long as you can write a driver that takes the data in from the physical layer and hands it to IP, you can do anything. So the original protocols all were tied the IP, the network layer to the physical layer, and so whenever you came up with something new, like a faster system, or you wanted to run it over satellite network, or pretty much anything that you could think of, you had to rewrite your whole protocol stack. So by putting things into layers, we can now focus on the physical layer people developing physical layer stuff and just having an interface to the IP layer, which means when we go from 10 megabit Ethernet to 100 megabit Ethernet to gigabit speed Ethernet to 10 gig Ethernet to now 40 and 100 gig Ethernet is just one example. We don't need to rewrite the whole network. The only thing that needs to communicate with each other are that single hop, and IP takes care of the fact that it got from one hop to the next hop, which may be a completely different protocol. So we can go from a gigabit speed local network to a DSL line to a 10 gig Ethernet backbone to a satellite network in the middle to get to an oil rig to a local network on the other side is maybe 100 megabit Ethernet. So each hop, as long as that hop can communicate with each other, that data is then just becomes an IP packet that goes on to the next hop, and each hop can be completely independent of each other. And that means we can add whatever sort of physical layer we want because we control those two end nodes, and above that we can add, we can create whatever sort of applications we want because we have a network that can communicate with each other. All of this nowadays is just ubiquitous. It's all there, it all works. It may not be ideal. There are a lot of things that could have been done differently, could have been done better if we knew the internet was going to have billions of nodes on it instead of thousands of nodes. And was going to be going at 100 gigabits per second instead of 64 kilobits per second. But we have what we have, and it works very well. And now the whole world is connected, all because of this IP hourglass. So I think that comes to the end of today's presentation. Let me try to get back to where I was, so we can pull me back up again.
You're up.
So DC, just for future reference, I think you ought to put on a dark blue sweater and pretend that you are Mr. Rogers. Because you have that voice, man. It's just mesmerizing. What do you think, Tim? Did we do a job today? Did DC do what he said he was going to do?
Great job. I love the hourglass thing.
Yeah,
I've
that was
seen that
great.
before.
That was amazing, yeah.
That really puts it in perspective. It's really the translator from where we are remotely to the network or through the network to the end user. And as we talked earlier, right now everything is IPv4. or as I tell people, it's IPv4, BEFORE, because it is a combination of all from the very beginning. The next migration will be IPv6, and that's a long ways away, which will add a little bit more complexity. But your perspective today was wonderful because it like you pointed out earlier, a lot of people, know about stuff. They know how to hook up cables, but they don't understand the physics behind even the cable, an RG cable or an Ethernet cable. And it's getting more complex. But the nice thing about IP, it's that ubiquitous translator that gets us into the internet, into any network, and out of it. So
and you're completely right about IPv6. When you look at that hourglass, everything works because there's one layer that the whole world uses to communicate with each other, and that's IPv4. And IPv6 and IPv4 are not interoperable with each other, at least at their core. And so we end up with a completely separate hourglass of an IPv6 network that is not ubiquitous, and transitioning from one to another is a real nightmare. And I think that hourglass kind of shows why, because we have this one point in the middle of IPv4 that everyone depends on, and it's there. The people above it know it's there. The people below it know it's there, and it took a generation to build that. Switching over to something that's different and not backwards compatible just isn't easy.
Yeah, now I think the word you used was ubiquity, and
Yep.
IPv4 is the way it's written right now. It is ubiquitous. It'll handle anything, like you showed. It could come from a cable modem. It could come from Morse code. It could come from a camera. It could come from any interface, and it can handle it, and it can push it out to the network. And at the other end, it can go anywhere it wants to go. It can go through other satellites. It can go through other transport domains. Wi-Fi is a separate transport domain, so you've got, WAN's a different transport domain. Every device kind of adds a little bit down on the bottom, but the universal key is IP and TCP. That handles it all, no matter what's below it, no matter what's above it.
Yeah.
Right.
So it's key, and I love the way you did it.
Yeah. So, being a Woody Allen fan, I was going to name this episode "Everything You Wanted to Know About TCP/IP But Afraid to Ask." But that's really what it is. So I encourage our readers out there to ask questions. This is the time. This is the whole point about Sharkfest.tv is we want to go back to the fundamentals. So if you have some questions, some comments, feel free to put that on our Love My Tool blog. This video is going to show up there. Or if you want, just go to the YouTube video and put comments there as well. We can answer those. DC would answer them. Tim will answer them, and our writers can answer them. So don't be afraid to do that. DC, why don't we spend a few seconds talk about what you have planned for the next episode?
I need to go back to my notes real quickly to see. So the next episode is an overview of TCP/IP. And the different components of TCP/IP, because it's not just TCP and IP. There's things like ARP and other SNMP, things like that are all part of it. So I want to give an overview of TCP/IP in general before I start getting into the details of the important pieces.
So we have the TCP/IP hourglass, and now we're going to do the TCP/IP onion, right? We're going to peel it one layer at a time.
That's a great way of thinking of it. Yes.
Yeah.
So I think that will be the title of the next episode, the TCP/IP onion.
All right. So so we're going to close the show.
Will we cry?
Tim, go ahead. Tim, you have some comments?
Yeah. When people start looking at protocols, one thing I tell people to do is go to Wireshark and download Wireshark. It's a great tool. And you can go to Wireshark University, Lord Chapel's place, and there's a plethora of trace files out there that you can look at. Most of them are two-way, or full duplex, as we used to refer to it as. but it will give you an idea how functionally TCP and IP are working in a network. You can actually see the packets, see the simple exchanges, and especially when we go to the next step, we start looking at ARPs and we look at the other layered protocols underneath TCP IP that are part and parcel to it. So you just go to wireshark.org, download Wireshark. They got a ton of trace files on there if you want to get, see what it really looks like in the real world, or Wireshark University. And there's a ton of other really good libraries of trace files out there.
Yeah.
And what I'm going to do for DC is I'm going to try to get a collection of trace files put together, and we'll put the links or put them on our website so people can, especially next week when we start, or next time we do ARP and we start looking at the different protocols, DNS, interchange protocols, to get it lined up with the internet and permission granted to communicate. There's a lot of little nuances in there, so I'll definitely try to help you put together some of that so you can we can give it out to people.
Yeah, I think that's right. I think Tim said it, that there are a lot of people. Tim mentioned Laurel, and there's so many people who have benefited from the Wireshark community and are contributing to it, and we're just trying to do our part. I had interviewed Gerald Combs a number of times. Tim knows Gerald forever, and one of the things that I noticed about Gerald is that without Gerald, we wouldn't even be here talking about Sharkfest. But the thing about Gerald is that he doesn't like to talk about himself, right? We all know that. He's a very difficult person to interview. He just doesn't open up. He doesn't like to talk about it, and there's a reason for that. I believe that I think in his mind, even though he never said it, in his mind, he's thinking, well, don't flatter me. The best way to appreciate what I do or what other people do is to contribute, right? Take your energy and put it back into the community, and that's how he is, and we admire that. And I think that's deep down, that's what Tim and I wanted to do. Is we really want to contribute back. We do it every day. That's why we enjoy what we do. And I think Sharkfest TV is not only a tribute to the people who contribute to Wireshark, it's our own little way, and today with DC's help, it's our own little way to contribute back. Is that right, Tim?
Yeah, and also I think that every technology needs a common base, somewhere you can run to ask the questions. You can go on the internet and ask a question, but if you're in the Wireshark community, just like you said, if someone puts a question on Love My Tool, someone's going to answer it, okay? And it ranges from people on the low end like me to really smart people like DC or Gerald or somebody else will step in. And that's really what Wireshark is. It's not just a tool, it's a community. And so that we're trying to promote people having at least a basis of understanding that there is a tool out there. It's a reliable tool. They can use it to understand a lot more. It's like reading a book. You can read the words, Everybody remembers their first chemistry experiment, unless they didn't survive it.
Then they remember it really well.
Yeah, well, they somewhere else, not in this world. But you finally get a chance to, I'm going to mix all this up, and it's going to do something, And that's really what this is all about. I mean, DC's doing a great job. DC's been around in this industry. He's an expert in this area, and but the tool, the Wireshark tool, will give you that visibility. We're so visual these days, it's almost gotten when you go to court, if you don't have a video, they're like, you can't be guilty if you don't have a video, So, this is really important because people just don't, and I get a chance to teach periodically, and the students just don't get a sense of the basics anymore. When DC and I went through engineering school, we started out, what was an ohm, and then we went through every physics law, Kirchhoff's law, you name it, everything, before we understood the fundamentals. Even that a piece of wire is not simply a conductor. It's a radiator, it has capacitance, has inductance. Like my famous argument I think I've talked about once before is where a guy hooked two ends to a cable and wanted to move his analyzer to his desk, and it was only 30 or 40 feet, but all of a sudden his analyzer wouldn't work. And I said, well, how long is the cable? He said, it doesn't matter. It's just wire. and it turned out to be an 8,000-foot roll of Cat5 cable. No wonder the analyzer didn't work. And he argued with me. He said, "That's great. That's stupid." He says, "Just wire." And then I had to explain to him all the other nuances of what that just wire was. And starting with the fundamentals of TCP/IP is the only way you will understand networking. You can't jump at the application or the transport layers. You have to start at the bottom and understand it one step at a time. Then it all makes sense. And that's why I'm delighted to have DC do this. This is great.
Okay, so once again, I want to thank DC for his effort today, his contribution. And you did mention, DC, that you have written a book on this. Where would they go to find it?
That's a good question. I think it's out of print at this point. I need to look that up and get back to you. It was also focused specifically on the needs of satellite engineers. So it may not be the perfect thing for people listening to this.
Well, time to rewrite that book then.
Yes.
In his spare time.
Okay, thank you, DC. And we look forward to having you come back, hopefully next week.
Looking forward to it.
Yeah. You know, by the way, you created your you created your own. You create a problem because you help you've been contributing so much to the LMTV format that we're fully booked for the next one.
That's great.
But we'll find a place for you. We'll find time for you. Don't worry.
One last thing, by the way, everybody, DC works with a company called Apposite.
Yes.
And if you want to know about emulation, they're the people to talk to. Don't deploy it. Test it before you destroy it. That's been my motto.
Yeah.
You know, the old story is you hook up a bunch of lights and everything looks good, the wiring's great, and you flip the switch and it's only on a 1 amp breaker or 10 amp breaker, you blow the breaker. Today, if you lose your network, you won't be working there much longer. So test it before you deploy it.
And DC, if people are interested in your product and they want to get a evaluation copy, how would they do that?
Oh, well, thanks for the pitch for our company product. So yes, I'm with Apposite Technologies, and if you're interested in learning more about how to test your applications over different networks, please look at our website at Apposite APPOSITE -tech.com.
Thank you. Or you can just come to I Love My Tool and click on the Apposite Tech
That's right.
icon. Tim and I only get 10%.
And actually see a demo of our products.
Yeah, that's right. Okay, so with that, we bid you goodbye. We'll see you next week. We actually have a new sponsor. It's the company behind Interop, and we're gonna do an interview with one of the key contributing member. So we'll see you next week, and thank you for joining us. And go out there and be good. Thank you. Bye bye.